Today we're going to talk about differential equations with logistical equations and Euler's method. We can look at the graph I made here. So basically differential equations is the overarching genre, and logistical equations are a type of differential equations, and Euler's method is just a way to approximate the value. Okay, now let's look at the worksheet. Sometimes the question will only give you, say, u primed or y prime. It doesn't give you the du over dt. So you would sometimes just have to assume, because we're doing differential equations, that this is over dt, because there's a t right here. We're doing the same thing, separating the u and the t, but we get an integral of tan t. Sometimes trig identities will pop up, so we will have to remember all the integrals of tangent, as well as, I would say, definitely remember all the trig identities as well. Simplifying all this down, you would get u squared here, and then remember always when you take the square root of both sides, there needs to be a plus or minus. This one, the separation may not be as obvious as the other ones, because we have both terms within one exponent. So you always, every time we look at a differential equation, always try and find if there's any possible way to separate the two. Now we know that exponents can be separated if they're adding or dividing by simply taking them out into two separate exponents with separate bases. The same thing, putting the two terms on each side and taking the integral, simplifying that down. Remember the plus c, and taking the negative over. When you take the negative over, you might feel like you have to change the plus c into subtracted by c, but as -1 is a constant as well, timing c by -1 is the same as keeping it as plus c. Number 5, you obviously first off isolate t and x. However, when you see this, when you're looking at an integral, you always want to think about the different ways of attacking it. You think of du, always think ahead, thinking of what would the derivative. So number 7, it gives you the differential equation, a point in the particular solution, as well as the local minimum and its x value, and it asks for you for your y value. Now, this one, you might think that you have to solve for the particular solution, but remember what the slope is, at the local minimum. And remembering that this, we represent it in a different form. It's still the slope, so slope in this case, at this point, it would be 0. And since we're given the x value at this point already, which is right here, the only thing we have to do is plug that in and plug 0 in as the slope, and solve for y, which is that. Sometimes, questions would give in extra information, such as this one, just try to throw you off. Just simply remember what everything is. Usually these questions, they challenge you conceptually, making sure you know exactly what you're solving for. This one is a fairly generic problem asking you to solve for the particular solution. You can plug in this at any point during this process of the simplification, but just always remember that the c you get from plugging 2 and -1 into that c you get, you always want to plug that c back in to the place where you plugged 2 and -1 in from. So here's an example of Euler's method. So they would give you the derivative function, and as well as a point on the particular solution, as well as always look for when you read step sizes. So it could be saying explicitly, step size of 0.5, or it could be asking you, in this case, 2 steps from 0 to 1/2. So that would be 1/4 for the step size. And Euler's method, they usually tell you to approximate using that method, as here it says, use Euler's method. And also, another thing is, this was given in the calc section of an AP test. Even though I asked for calc, I think it's always best to leave it in the exact value as seen here. If you can, leave it in fractions. So, taking the first derivative, we would get 2, and plugging that into the slope formula, y subtracted by the initial y equals slope times the x you're using as a step, which is 1/4, subtract by 0, and get a new y value. Now use that new y value and the new x value, which you're solving this y value at, to get the new slope. And with that new slope, plug it into this slope form with x to 1/2 is the point that y you want to look at, and y you would get, simplifying all that down, -11/32. Number 10 is another example of Eulers. Eulers are usually pretty straightforward. There's usually just one way to do it. You just plug things in. And however, this one asks you to solve for the approximation using different step sizes. Fractions are usually the ones where you can easily keep the exact value. Decimals, it could get very, very long. Number 11 asks for when is the population growing the fastest, and it gives you the equation for the population. So by previous knowledge, we know that this is the maximum slope, which is p double prime equal to 0, which is the point of inflection. So when you look at this graph, the point of inflection always happens right in the middle between 0 and k, so k over 2. That's when the point of inflection always happens on the logistics graph. We can memorize that, where we can always derive that, which would take more time, but it's possible. At any point during this calculation, however, we can always plug that into the calculator, plugging this side into the calculator and plugging that side in the calculator in the graphing section, and finding the intersection, or we could simplify it down all the way and trying to just find it in a calculator with the regular calculating function. So number 12 gives you the p prime function as well as the initial function. It asks for you to solve for when the population is double that of initial, which is 2000. So this p prime is given in the alternative form, where that is the k. And as I mentioned earlier, to get the original k from the other formula, so we can convert it to p, t, because it's asking for what the population is, we just time the alternative k, small k, by the big K, so that'll be 5,000 times the alternative k, which is that value, and we could get 0.05, and putting into the PT equation, and simplify that down all the way, and you get T is approximately 19.617. 13 gives you that the max population is 2,000 wolves, which in terms of biology and animal species, as time increases, it always approaches this value, so that is its maximum capacity, sometimes it will be called. And also says that there are already 25 wolves, so it means basically, always note down things as you go through the problem. That means like P initial equals 25, and the rate of growth of the population, which means P prime at T equals 0, so P prime 0 equals 5. So it's asking for P prime. We already know the model for P prime. It's Kp times 1 subtracted by P over K. However, it does give you P, but you don't know what K is. So you would try to find a set of values for P prime of T and T. So it's given you that rate of growth P prime of T equals 5 when it's T equals to 0. Always remember that T is not part of the P prime equation, at least not obviously so. Instead, when you look at T equals 0, you should think about the population at T equals 0, because the P prime T formula has population in the equation rather than T. So when T equals 0, it's actually given you that the population is 25. So you would plug 25 into the formula and set that equal to the P prime of T given, which is 5. And so for K, and then now you have K, you can plug 100 in to solve for what the P prime T is. So plugging all that in, you get this. T right here represents an actual time, not as a variable. Sometimes you would see it represented as, say, P prime of C, because we're representing an actual value, not the variable. And in part B, because we already extracted the values right here, and we already know the K, we can just plug everything into the formula and look for population equals 150. And we plug that in, simplify all down, and all that gets you T equals 13.32. Number 14, someone can really easily get tricked up by the form of this question because it looks so similar to the logistic model, but then it is not, because we don't have the B up here as the model would need. So even if it's really close, it's not, unless it's exactly it, or somehow you can simplify or change around the equation to get the model. So this will be just a simple differential equation. So sometimes word problems would add in statements just for the purpose of eliminating any doubt, because in this case, someone might think about the ball actually hitting the ground, because that V is following a logistical model, terminal velocity, which is basically k, is 50 meters per second. Sometimes they would mix in certain terminologies, such as terminal velocity, carrying capacity. All of them are just different ways of telling you what k is. Again, as you read it, jot down things as you read. So, and when you get a bunch of variables, always think about can you plug it in, and if you plug it in, what's missing? If we think about it, if we want to plug everything, the thing that's missing is the k value. So in order to get that, we already have a set of values for the population model. So we just plug that in order to get k. Always leave k as its exact value. If you once now you get the k value, you can plug t in to get the velocity. And a lot of times, unless mentioned so, settings of a separate part of the question will be independent of the previous part. So this time the question gives you two sets of v and time data, so 40 and 50, 45 and 55, and you'll be thinking, oh wait, where's the initial value? Given two sets of different times, you can always set one as the initial. In case 50 seconds would be the initial time, and then v0 will be 40, and v5 will be 45. So now you can use that value as well as finding a with the initial value to find k. Now k would be that. As I said, leave it as it is and don't approximate the value in decimals. Now that we find the v formula, we can plug things in, plug the time in to the equation, and we would get what the velocity is. Number 16 definitely has a concept that's very hard to wrap your brains around, but we have to take in mind is that e may not always be the independent variable. Number 16 also states the relation with simply just words, so the skill of jotting things down as you go through the words and sentences is definitely an important skill that will help you. I said that dt over dv is directly related, meaning that is a constant times t. Inversely related, on the other hand, would be, say, dt over dv equals k times 1 over t. And this question really challenges you to think simply in terms of math. So like change in time over velocity, which is, as I mentioned, dt over dv is 10 when t equals 100, and t, time, is 100 seconds when the velocity is 50 meters per second. And that's basically the mother function. Now, number 8 just asks you to make a slope field in a certain interval with a certain amount of points. So 3 by 3, so 3 points, 9 total points. And interval just indicates where these points that you need to draw the slopes are. And first off, we have to find exactly what the slopes are in the slope formula. We get that, from the stuff we have. Just think of the equation and think of how you could plug all these values into it in order to solve for something in the equation. So in this case, we already given the t, so we plug t in, and plug the dt over dv in, and we solve for k, and now we can get the function for dt over dv. And now we can make the slope field by simply plugging in the t value and getting the slope at each t value. One way I find to make an accurate slope without using anything complicated is simply, making little dots and then connecting these two dots. So sideways 1, up 2, this would be a slope of positive 2. Part B asks for the particular solution of the amount of time. So you could recognize already that this is the form of exponential model. So then you could jump straight here, or you could go through the differential equation solving. To this point, you always got to remember at what point of the solving process you are at. Now you have the general equation. Now you have to plug in a specific point in order to get the particular solution by finding c. So we already know that the time is 100 when the velocity is 50. So t equals 100 and velocity equals 50. So simplifying that down, c, we get this when plugging c back into the t equation. When you see something of the same base, it's always good to put them under the same base. So it's another step of simplification.